A nice change of pace here in Chapter 16. We've done a little introduction to NMR at the end of last semester when we used the benchtop NMR in OChem 1 lab, but now we're going to get to know it in great gory detail. There will be several mini lectures to this chapter, and I'll try to keep them pretty short and sweet. Or at least short. Alright, so anyhow, intro and overview. We learned last semester that spectroscopy is all about electromagnetic radiation, EMR for short, and that's just energy. And energy interacts with matter. So, Nmr Spectroscopy is just another area of spectroscopy where the electromagnetic radiation of Nmr Spectroscopy is in the radio frequency range. So when you look at the whole big picture, the whole spectrum of electromagnetic radiation, you see that radio frequency radiation is way down at the far end of the electromagnetic spectrum, where they're low frequency and really long wavelength radiation. So that means small energy. So we've learned quite a bit of spectroscopy already. We've learned IR and UV. So what's the difference with them, with those kinds of spectroscopy and NMR? Well, IR transition was that when the molecule or the matter absorbed energy, the bonds either stretch or bend, and that led us to information about functional groups. So that's what we learned, functionality. Well, how about UV vis? What about that? Well, with UV vis, the energy transition, in other words, what's going on when the molecule or matter absorbs energy, is that an electron is promoted from a filled high energy orbital into an empty unoccupied orbital. So like from the HOMO to the LUMO. And that promotion of an electron told us about chromophores. So a lot of extended conjugation. Those kinds of molecules show up in the UV vis. Now, what about NMR? NMR is really kind of bizarre. The molecules that absorb that teeny amount of energy in the NMR radio frequency range of the electromagnetic spectrum are undergoing what we call a nuclear spin flip. So basically, as usual, when the material absorbs energy whose frequency of radiation matches this energy gap, whatever that energy gap translates into, and it's the spin flip, that energy is absorbed. That's recorded on a spectrum, and we get information from that spectrum. The information that's so useful is that it tells us all about the carbon-hydrogen skeleton, and that's particularly good because it complements IR so well. IR tells us about functionality, NMR tells us about carbons and hydrogens, which, IR is pretty useless at. Alright, so more detail into this transition. How does this work? Well, certain kinds of nuclei, when they spin, they generate a magnetic moment. So here's a picture of a cute little hydrogen nucleus, and what you can imagine is that it's spinning around and around. That spin creates a little internal magnet, teeny tiny magnet around that nucleus. And you can imagine that magnetic moment could be pointing up, straight up. That would be called the alpha state. It could be pointing straight down. That's the beta state. So those are kind of the two extremes. Really, these nuclei in pick a molecule, any molecule, they're just all randomly spinning around and oriented any which way. In that case, what you can see here is that in terms of energy, those little spinning magnets are all what we call degenerate. They all are exactly the same energy. None is higher energy than the other. However, that's only when there is no external magnetic field, because as you can imagine, once you place these little spinning magnets in an external magnetic field, there's going to be a differentiation in their energy levels, because those little spinning magnets that are oriented with the external magnetic field are going to be in a lower energy state than those guys who are bucking the field, if you will. Those little spinning nuclei magnetic moments that are opposing the external magnetic field are definitely higher energy, and bottom line is that you have this gap here that allows for you to record a spectrum. That's the energy gap that is the critical piece to any kind of spectroscopy. There has to be absorption of energy that corresponds to the wavelength / frequency of the electromagnetic radiation spectrum. So here is the key Nmr equation that describes this phenomenon, that energy gap is related to two important things here. Number one, the magnetic field. So B stands for the magnetic field. You're literally putting this inside a magnet. So B sub external stands for the strength of that external magnetic field. H is Planck's constant, 2 pi, we know what that is. And then this little guy is the gyromagnetic ratio. It's just a constant that's unique to each particular NMR active nucleus. So bottom line here is that the energy gap that is formed upon putting your sample into a magnet is proportional to the strength of that magnet. The other important thing is that energy difference is teeny tiny, very, very small energy difference. All right, but this figure out of your textbook does a nice job of illustrating that as the strength of the external magnet increases, the gap increases, and that leads to greater sensitivity in your spectrum, better resolution, and blah, 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 blah. But the important message I want you to get is knowing that the energy gap depends on the magnet strength. That's the 4-star message. All right, well, what do we get? This is what we get. Some of you who are in OChem lab last semester saw something like this. This is a typical proton NMR spectrum. And I should point out right now that proton doesn't mean H plus in NMR spectroscopy. It just means the regular old hydrogen atom. It's embedded in the lingo. So this has nothing to do with acid-base chemistry. The other thing I should tell you is that when I'm going through this chapter, 95% of this focus will be on proton NMR. The other important nucleus that we pay attention to in organic chemistry is, surprise, carbon, C13. So I really don't cover C13 in the mini lectures because it's really straightforward. If you can master proton NMR spectroscopy, C13 is a piece of cake. All right, so what do we see in a typical proton NMR spectrum? Well, some of this will be a little redundant from last semester, but number one, the number of signals that we see tells us how many different types of hydrogens there are in the molecule. So when we look at the spectrum, we can see that there are 4 different sets of hydrogens. Where those signals show up, around 1, around 4, around 7, and around 8, is diagnostic. It tells the practitioner immediately what kind of environment those hydrogens are in. This guy is a super useful piece of information, and it's called the integral for obvious reasons. It tells you the number of hydrogens associated with each signal. So while I can't say exactly how many hydrogens are associated with that signal, I can tell you, since this distance is pretty much the same as this distance, then these 2 sets of signals are coming from the same number. So if this is 2 hydrogens, this one is also 2 hydrogens. If this one is 3 hydrogens, this one is also 3 hydrogens, etc. Then you'll notice that these signals are quite different looking. This one is a nice looking kind of a three-pronged deal. This is a four-pronged deal. This is a mess. This is also a mess. Those patterns are very, very useful. They tell us what number of hydrogens is next door. And finally, the gap between these little patterns is also diagnostic. We're going to go through each one of these pieces of information in great gory detail. Now, the good news, bad news is that not all nuclei show up in NMR. In order for a nucleus to be quote-unquote NMR active, it either has to have an odd number of protons, an odd number of neutrons, or both. So the good news is, especially for us organic chemists, proton and C13, yes, show up in the NMR. C12 does not show up. Oxygen 16 does not show up. So you may think, well, that's too bad, but actually it keeps things simple. All right, so now we're going to skip around a little bit. Shielding is going to be covered in the next mini lecture. What we're going to talk about primarily symmetry right now to help you understand how to look at a molecule and predict what its NMR spectrum is going to look like. So here's good old-fashioned ethyl ether. Now remember, I'm talking strictly about proton NMR. My question is, how many different kinds of hydrogens do I have in this molecule? Well, I have some CH2s and I have some CH3s. So it would appear that I have H sub A and H sub B in this particular molecule, and in fact my proton NMR spectrum of diethyl ether is going to consist of two sets of signals. Those signals having to do with H sub A and those signals having to do with H sub B. But what about, now I've got ethyl isopropyl ether. Symmetry is absolutely geometrically rock solid, right? When I know something's symmetrical, that means that if I kind of plot it out onto some kind of grid, then this has to match up exactly with this, and this has to match up exactly with that, which it doesn't. I have destroyed the symmetry in this molecule by adding this extra methyl group. So how many different kinds of hydrogens do I have now? Well, those three hydrogens are all identical as far as I can tell. And these two hydrogens are different from the methyl group on the left, that's for sure. Certainly, this methine is unique. There are no other methynes in the molecule. But the real question is, how about these other methyl groups? Are those 6 hydrogens all the same? Well, no. By symmetry, they are not. In other words, this guy is unique compared to the one circled in red. So this would have to be D. What about this guy? Is that E? Well, then we have to get into a little bit more detail. So erase all our strokes. Remember that molecules are three-dimensional beasts. And when I look at the three-dimensional nature of this particular molecule, by symmetry, I could put a nice plane right down that oxygen-carbon-hydrogen bond angle. And what that would do is show me that these two methyl groups are in fact symmetrical. They're equally distributed on either side of that orange plane. So going back to our previous slide, that means when I look at this molecule, I have A, B, C, D, D. These are all identical in terms of symmetry, and I would expect to see 4 sets of signals for that particular ether and 2 for the one on the left. So symmetry really helps us predict what we're going to expect to see in the proton NMR spectrum. Alright, so we're going to recap at this point. This is getting to be enough. Certain atomic nuclei are NMR active, meaning they possess spin and can do this spin flip thing. That includes proton and C13. Only when I put those molecules that have protons and C13 nuclei in them will I be able to see this gap in energy that allows a spectrum to be recorded. So I put this in the poles of a magnet, run it through a scan of radio frequency energy, and then I get this spectrum, which tells us so much information about the connectivity of the molecule, the different kinds of hydrogens, the symmetry of the molecule, the number of hydrogens associated with each signal, and even how many hydrogens are sitting next door to each one. Amazing stuff. But now, very important, how is duct tape like the Force? Well, it has a dark side, it has a light side, and it holds the universe together. Alright, see you in class.